Thank you, everybody, for being on today's webinar titled Correlating Experimental Test Data and FE Results. The agenda for today's webinar is going to be a brief introduction to who we are, then leading into discussions about virtual strain gauges and how we can then correlate those virtual strain gauges with measured test results. We'll cover a couple of additional correlation topics, wrap things up with a summary, and then have a Q&A session at the end of today's webinar. So before we get started, I'd like to provide a brief introduction of who we are. Finite is a division of HBM. You may be more familiar with our software brands ReliaSoft, which is a software analysis tool for reliability, and also nCode, which is a software analysis tool for fatigue and durability. But Finite does more than just that. We offer training services on these software products, as well as the theory behind them. And we offer services to our customers for things like material testing at our own facilities, as well as solutions for asset management and solutions for design, development, and testing. Within our brands of ReliaSoft and nCode, we've got quite a few different products covering a wide variety of tools that would allow you to address any kind of reliability or durability needs. For today's webinar, we're going to very briefly mention Weibel, which is one of the ReliaSoft products, as well as VibeSys and CliffWorks. But for the most part, today's topic is really going to focus on some tools within the DesignLife product. The objectives for today's today's webinar is going to be how we can generate virtual strain gauge results from FE models. We're then going to learn how we can compare those to measured strain gauge results. And at the very end, we're going to cover a couple of slides where we introduce a couple of additional topics focusing on modal characteristics of a structure and how we might be able to address variability in results. So to begin with, let's take a look at some virtual strain gauges. And we can ask the question, what is the value of a virtual strain gauge? There's quite a few different things we can do with this. For example, you could gather strain results from different variations of geometry from an FE model. We can do some sensitivity studies on those types of things. We could, in fact, build a load transducer. We could infer loads from virtual strain gauges. This becomes really powerful in scenarios where you want to make direct load measurements, but because of the structure, because of the configuration of the test article or the way it's being used, it's not practical to use an actual load cell. So we can instrument our own parts and then generate loads from that, or recreate loads from that. Lastly, we could correlate strain gauge results with measured results, and that's going to be the focus of today. We can see that we've got a physical test article in this upper image. It's been instrumented with gauges, and we have a virtual model down below that has some virtual strain gauges. And the analysis can allow us to overlay those gauge results. So let's talk a little bit more about the virtual strain gauge and how it is actually used inside of nCode. The virtual strain gauge is actually going to be a tool within the FE input glyph, and we're going to see a demonstration of this later, so you guys will get a chance to see that. We can see it circled right here. And upon clicking on that, you're going to see an interface that then allows you to begin defining virtual strain gauges on your FE model. And you can think of this as very analogous to placing strain gauges onto a physical test article. We've got different types of strain gauges that we can place on the FE model. We can do singles as well as rosettes. And once those have been placed, we can control the orientation of those strain gauges. And we've got a number of different ways in which we can control that orientation. Sometimes we can align it along the XYZ coordinates. We can align it along nodes that are user-defined, and we can also enter an angle that is going to be from one of those two. And again, we'll see how that's done in the demonstration in just a moment. So now that we've placed a virtual strain gauge on our FE model, now we have to build a process that's going to allow us to then correlate that to some measured test data. So let's talk a little bit about two common uses for correlating or for using strain gauges, one being correlation and the other one doing hotspot strain gauging. For correlation purposes, what we'd really like to do is avoid areas of high stress concentration or high strains. We're going to be focusing on the areas with low stress gradients, and we can see summarized here down in the table. If we are doing correlation with FE, again, nominal strain areas, the advantage here are virtual strains tend to become insensitive to the location. We could perhaps move that strain gauge to an adjacent element, and we're going to get very similar results. For the structural analysis, perhaps if we're doing some hotspots, the actual objective there is to capture some of those peak strains. Perhaps we're going to be doing some durability calculations on that. So in those particular examples, we're going to be trying to calculate those hotspots. But for today, what we really want to be doing is correlating with FE and looking at some of those nominal areas. We're going to build a process that looks a lot like this. This is what I'll do in the demonstration for you. And once this process is built, it's going to give us a number of ways in which we can compare what is our measured strain gauge data with virtual strain gauge data. And that's going to be coming out of this pipe right here from our virtual strain gauge analysis glyph. So once we bring those both into a display glyph like we see here on the right, we can then begin to answer questions about how well this might be correlated. We can compare those in a number of ways. And the next series of slides, we're going to see different ways in which we can take this strain gauge data, whether it's virtual or measured, and make some comparisons on that. So one of the things you might want to ask is, are these similar in shape? So if you just zoom out and look at the entire time history of your virtual and measured strain gauge data, do they appear to be similar in shape? If yes, like we see here on the left, we could then make the assumption that we probably are making some progress towards correlating it. We see something like this, and we can clearly see, without really even having to zoom in and look at smaller sections of the time series data, that we've got pretty poor correlation. So something is going on here where we didn't generate virtual strain histories. We can also look at things like polarity. So if we have zoomed in just a little bit to our virtual strain histories and also our measured strain histories, we could begin to see if when we have an upward trend, if that occurs in the other signal as well. Over here you can see that there is not polarity, so in this particular example we could say that we don't have a very strong correlation. Another way of looking at this polarity is if we were to cross-plot those two channels. If the polarity is correct, we're going to tend to see something along a diagonal right here. And if the polarity has been flipped, we would see something perhaps like this, a diagonal going in the other direction. We can also take into consideration the magnitudes. And when looking at magnitudes, one of the first things you can look at is simply the auto-scaled minimum and maximum values you see on the vertical axis. Are these values similar from the measured versus the virtual strain histories? Over here you can see that there is some difference, and because of that, these are perhaps not correlating as well. Lastly, what we can do is look for areas of inactivity versus activity in our time history data. In this first example on the left, we see at the very end of the test, there's in the measured data some noise, but what appears to be some flat line. And in the virtual, we have a flat line as well. So that is pretty much in agreement there, where we have some inactivity. Perhaps here we could say we have some lower level activity. Here we might have some transient activity. And then over on the right, we can see we have a scenario where things are not lining up. Now, this is perhaps a bit exaggerated, but we can definitely see that something is occurring in the time domain that does not appear in the other channel. So one other way in which we can determine if we've got good correlation or not. Now, what I'd like to do is actually build for you a case study and then do this demonstration for you in the nCode software. So what we're trying to do here again is to correlate measured FE results with measured data. We have a structure that we have done an FE analysis on, and we also have a similar structure as a physical test part that we've taken out in the field. And this particular one has been instrumented with a load cell. This load cell, you can think of it as a wheel force transducer, where we've measured X, Y, Z forces as well as X, Y, and Z moments. And we've also collected strain histories at a particular location on this structure. And if I move my mouse, you'll see that it was in this area right here. And we took that out on the test track and then collected some measured data. Collected both loads and strains on the physical test part. So what I'm going to do for you is actually build this process right here, where we take that FE model, bring in the measured time series data, and output virtual strain gauge data, and then compare it with measured strain gauge data. So let me go ahead and go into the nCode environment. What we have here is the nCode environment, and I've actually already navigated to a directory that contains those models and time series data. So I'm going to drag out this model here, and if I enlarge it, I'll just rotate this around a little bit for you so you can see. This is the suspension component that has been instrumented as a physical part on vehicle. And the first thing that I want to do is place a virtual strain gauge in this area right here. So to do that, I'm going to click on the virtual strain gauge tool. And what I'd like to do with this menu here is to add a strain gauge. You can see here on type, we have the ability to select different types of gauges. So I'm going to stick with the single, and we can apply it in several locations. What I'd like to do is apply it to the element centroid, and I'm going to graphically pick it. So I'm going to select this tab, just click on the pick button, and as I mouse over my model now, you can see it is highlighting the element that is beneath my cursor. So I'm going to place it right here. And the orientation, I'm going to control my orientation initially just to align it along the x-axis. So you can see I've placed a 1 here and a 0 in the other two global coordinate directions. If we hit the apply button, we've now created a gauge. Now, initially it shows up, the graphical representation is pretty small. Let me enlarge that for you so we can see it. So we'll just go into the properties. And underneath the model parameters, I have the ability to enlarge the graphical representation of that gauge. And now we can see the gauge a little more clearly. Just to demonstrate, we can rotate that gauge about a normal vector to the surface it's been placed on, just by sliding this slide bar right here. I'm going to leave it, however, in the X direction, and we're just going to hit the OK button. And we can close this window and minimize this one. And now what we'll need to do is bring out the wheel forces. So let's drag that out on the workspace. And let me just show you those briefly. We've got 6 channels of measured data. The first 3 are going to be the forces in the X, Y, and Z directions. And those are followed by the moments in the X, Y, and Z directions here. And what I would like to do then is bring all that information together inside of a virtual strain gauge glyph, which is on the DesignLife glyph palette. So let's drag that out onto the workspace, and connecting these pipes allows me to bring the input information from both of these input glyphs into the virtual strain gauge glyph. Now there are a couple of extra things that we need to define here, and if I were to right click on the glyph, the first thing that I'd like to define is to assign a material. Unfortunately, we don't know the material that was used in FE just by looking at the FE results, so we need to define that here in nCode. And for a virtual strain gauge, we really just need to worry about things like the modulus. Therefore, I can pick pretty much any kind of steel, and I'm going to assign the steel to that entire FE model. And I do need to make a change in the loading as well. So let's go to load mapping. And before I make the change, I'll just point out a couple of key areas. What we're seeing here is a list of all 6 FE load cases that were solved for, and you can see that they have been named in a similar manner as the 6 channels of measured time series data. So we've got X, Y, and Z forces, as well as the X, Y, and Z moments. And by default, they have been paired up together. So just going in descending order, we've got our 6 load cases as well as our 6 channels. The one thing that I do need to change, though, it's very helpful if these FE load cases were solved with a unit load, where somebody might have applied 1 Newton in the X direction. But you can see, just by the name of that load case, that the user in this case had applied 1,000 Newtons. So I'm going to apply, in this divider column, 1,000 for each one of those, which effectively brings my FE stress results in line with a unit load, so that we can then combine them and the math comes out correctly when we apply our time series data. Let's just apply a divider of 1,000. That's placed 1,000 in the divider column there, and that is good to go. And the last thing we probably should have at the moment is a display so we can see our virtual strain histories. And now we can hit the run button. So what we're doing now is taking those inputs, bringing them into this virtual strain gauge glyph, and outputting the strains as that virtual strain gauge would see, oriented along the x-axis, the global x-axis for that model. What we can now do is grab our measured strain histories, and we can pipe those in so that they can be overlaid with the virtual strain histories. And what I'd like to do is just set this to display 2. And since I had just piped that information in, I actually need to rerun my process. I'll just hit the run button one more time. And now you can see we have in red the strain histories from the virtual strain gauge, and then in blue the strain histories from the measured strain gauge data. I'm actually going to copy this. We'll make 2 XY displays. I'm going to pipe the same information into both. And for the very first one, what we can do is we can actually overlay both of those signals. And if we zoom into an area here, getting a little bit closer, we can see that we've got extremely good correlation in this section of our time series data. Again, red being the virtual strain gauge, blue being the measured strain gauge data. So we have a good correlation in terms of phase. We've got good correlation in terms of magnitude. There are, however, cases where maybe we see some drift. Maybe some of these magnitudes aren't quite lining up, and that's going to happen. But for this particular set of data, I would say that we've got fairly good correlation. And the last thing that we could do, we might as well show it in this lower display, is we could look at a cross plot. So if you want to cross plot the virtual, which would be on the vertical axis, versus the physical measured strain gauge data on the horizontal axis, we can now see that most of those data points are aligning along a diagonal between those two, telling us that we do in fact have good polarity, which we could also see by looking in the time domain when we zoomed in. All right, let's go ahead and jump back into that PowerPoint and cover a couple of additional correlation topics. The first one that I'd like to talk to you about is something called experimental modal analysis. It's something that can be done in VibesYs inside of nCode. Everything that we've seen so far in the demonstration took an FE model where we made static assumptions and then with linear superposition scaled up and down stress states in each of those load cases as they were measured in the time domain. What we would like to do here is try and take into account the dynamic response of a structure. You can imagine things where you might have some sheet metal that is responding dynamically to the loading input. It's going to be important to, one, model that in FE, and then also understand that excitation on the test article. When we're trying to understand that excitation on the test article, it's going to be helpful to measure the inputs into the system as well as the response of that structure at some other location. And that response can be measured at a number of locations. When we do this, we can generate things like gain and phase plots in the frequency domain. And what we see in this particular screen capture is, in fact, the gain plot, and each one of these peaks represents what we might consider a natural frequency or a modal frequency. We can fit a curve through this signal as well, and the shape of each of these peaks would allow us to describe the modal damping. How much damping does each one of these mode shapes have? And if we had a sufficient number of accelerometers to measure the response at several different locations on our structure, we could then begin to describe the mode shape. And if we were to visualize, for example, a simple mode shape, you might first envision something like a guitar string. And as that guitar string is struck, one of the first mode shapes would be essentially an up-down gentle heaving. A higher order mode shape might be a sine wave where you see a single sine wave. And as you continue to go higher in the mode shapes, you're going to see more and more sine waves. And many times those are going to be smaller in amplitude as well. And the only way in which we can experimentally describe those mode shapes is if we had measured it in several locations along the guitar string or along the structure in which you're trying to characterize. The other additional topic that I'd like to cover with you guys is how we can account for variability in results. Now, this isn't so much about taking two time series signals and overlaying them on top of one another, but rather taking FE results for durability as well as measured results for durability and trying to compare them. Now, if we take a structure like we see here on the left and perform fatigue calculations inside of nCode, we might get a single answer, and that single answer might be something like we can perform 610 repeats of some event before we would expect a fatigue failure on that structure. We could attempt to do the same thing out in the field where we take a physical representation of this structure, put it on vehicle, put it through a test, and we might get a number back that says something like that survived 480 repeats of the simulation we tried to create in FE, but out in the real world. And it might be difficult to try and compare that. It might suggest that these do not correlate very well at all. But in fact, that is one of the challenges that we have when we only take a single measurement or a single failure out in the field. We know that there's going to be variability in those types of results, and the best thing to do there is to test a population of test specimens. That population of test specimens can then be analyzed inside of a tool like Weibull++ inside of Relisoft, where we can create a statistical model of the life data from the field, and based on the failure mechanism, there may be some statistical models that better fit that data than others. But once we've done that, we can then begin to apply things like confidence levels and look at things like the B50% life for a population of specimens. And now we can see that this number here is definitely starting to agree much better with some of the results that we got from FE. And this is all because we've now taken a population and accounted for the variability and looked at a more representative value from that population. All right, so what I'd like to do now is just begin to wrap things up with a summary. And that is to say that we can use nCode DesignLife to generate virtual strain gauge results. These results can then be compared with measured results. We need to remember, though, things like high stress concentrations typically are not very good for correlating purposes, correlating virtual and measured strain gauges. So it's best to avoid those areas. It's best to place your gauges in areas of nominal strain or stress. The gauge sensitivity to location and orientation can be easily evaluated inside of DesignLife. We can always go back to that virtual strain gauge and rotate it just a little bit and rerun our process and see how much the strain histories change. We can even relocate it to a different element. The modal FEA can be correlated with experimental modal analysis in nCode Vibesys. That was one of those additional topics we saw. And then the second additional topic we saw was that Weibel can be used to compare populations of life results in the field to a single simulation result.